So what I'm going to do today is that I want to cover or review the second software or a specific simulation software, the software we use for simulations in this course, right? And that would be OpenModelica. Now, what OpenModelica is, right? If you open the course page, right, on Moodle and scroll down all the way at the bottom, right, the section that I put as softwares and tools. I've been using Graph to make graphs, importing data, fitting lines. We've been using Tracker, obviously, for the softwares. You know that, to track the objects from videos. Now we're going to use OpenModelica. We're going to use this for probably 2 or 3 of our projects, especially the final project also is going to use or is going to need OpenModelica for simulation. What OpenModelica is, I put a PDF file there, introduction and installation of OpenModelica. Right? I'm just going to open that. Right? You can also take a look at that. OpenModelica is pretty much an open source software, and this software is written based on or using Modelica language, or it is based on Modelica language. Right? What is Modelica language? A specific language. It's very well equipped when it comes to modeling engineering systems, and system engineers specifically use this language. And there are multiple even commercial software packages out there that they're using Modelica language, right? Some of them I mentioned here: Altair Active, Simpler, Simulation X. That's the one that I know relatively. It's famous. Maple Sim, Wolfram System Modeler. And the last one is OpenModelica. OpenModelica, the difference between OpenModelica and other ones is that other ones are not free. They are environments or software environments that are written based on Modelica, which is a programming language, but the software itself is not free. OpenModelica is free and open source. So that's the good thing about it, that anyone can download it and can use it, free of charge. So that's why we're going to use OpenModelica. But once you know how to use OpenModelica, you can easily transfer this knowledge when you are using any of these commercial software packages later on. Right? One of the famous ones again is Dimola or Dimola that I know. It's Dassault Systems use that. I put the link to each of them. You can just click on these links and take a look at those software packages. So that's the general idea. Right now, when I talk about the programming language, which is Modelica, I'm not specifically saying you're going to end up writing, you're going to end up coding. It's one of the main reasons I'm using OpenModelica as opposed to over MATLAB, because when it comes to MATLAB, you have to know coding. But here we are trying to avoid as much as possible coding and be more focused on the vibration aspect of the course, because this is mechanical vibrations, right? You have to have tools that are easy to use and we can implement them to make your simulations, modelings, and analysis as, I would say, easy as possible. So that's what I believe OpenModelica has an advantage over, I would say, MATLAB, at least in within the scope of this course when we are doing simulations. And I hope that you will see it that way. Now, to install this, the OpenModelica software, right, I put the link to a website, and depending on what operating system you're using, I put the links there. I personally have used Windows. I guess I also used Linux before, but I have never gone through the process for the Mac. I'll leave it to you. If you click on any of these, it takes you to a website, the OpenModelica website, and it gives you some, I would say, pretty good guidelines. Some of them are better, some of them are not very clear. So for Windows, for instance, if I click on the link I put there, this is the website for OpenModelica. It takes me to this page. Pretty much, if you go to the website itself, you can go to this page by going to Download and Windows. Now, always install official release. Right? Again, if you're using Windows, just click on that. It takes you to this directory that, depending on your Windows, is 64-bit or 4-bit or 32-bit. Most operating systems nowadays are 64-bit. So we click on that. Again, I've done this before. So OpenModelica .exe file. It's a relatively big file, 1.3 gigabytes. Right? You can just download it from there and pretty much install it. And installation should not be a problem. It should be a series of just click on next, next, and then install the software. In case of other operating systems, for instance, if you're using Linux or Mac, if you click on that, there is some explanation there, so I would highly encourage you to follow those explanations and try to install. Again, I have never done this on a Mac. Maybe I did it once a couple of years ago and it worked, but I will encourage you to follow these instructions. Usually they're pretty updated and they take care of all the possible problems you might face when you're installing it. All right, once you install the software, right, I also put a tutorial for you for OpenModelica for two specific systems. One of them is a free vibration of a spring mass system that you saw. Basically, that was the second system we looked at. Right? So we had the pendulum and then a spring mass system. That's how to model that system in OpenModelica. And the second one is a force vibration of a spring mass damper system. This is the system we covered in the last class. Spring mass damper, force vibration. Now I'll go through a couple of them. These ones, and I explain a couple more things in software that some of them you'll find in this tutorial, some of them you might not find. Now, once you install the software, I have it open here, and click on that. This is the first page you're going to see. OpenModelica has multiple libraries. I even explained that I did cover some of those free libraries, available libraries that are even written by other people. That's the good thing about open source free software packages, that other people can contribute to the software, right? To the whole process. Now it has multiple libraries. Some of them are already loaded when you install the software, when you install OpenModelica. Some of them you might end up downloading yourself, depending on what kind of application you have in mind. You might end up downloading the library. Again, in that PDF file that I put for installation, there is a section talking about libraries, and where we can take a look at the available libraries written by other people that you can use. Now, in this course, in the scope of this course, we're just going to use the libraries that are already loaded or in OpenModelica when you open the software. Now, on the left side, right, these are the libraries. You see the main part that we don't really, we don't have to be focused, or we don't need to talk about the libraries above. These first four libraries, these are specifically for the software itself. But the main set of libraries we're going to use are going to be the libraries under Modelica package, right? If you click on that and open this, or basically unroll this tree-shaped Modelica icon, right, you will see multiple libraries underneath. Now, these libraries, there are two libraries they're going to use for our simulation under these Modelica package. One of them is going to be the blocks library, which we're going to use 2 or 3 specific block from this blocks library, blocks library. And the other one would be the mechanics library. And underneath that, mainly focused on translation, right? The blocks that are available on the libraries or packages under this specific library translation. About the general, I would say, interface of the software, if you want to talk about, right, you have a message browser here that when you get a warning or you got errors, you'll see them at the bottom here. And pay attention that right now we are in the welcome page. There are different tabs here. There's a welcome tab, there's a modeling tab, there's a plotting tab, and there's a debugging tab. We're going to be moving between, well, going from welcome tab, which we don't really have that much to do on this, except defining the new model, going to modeling tab, and from there to plotting tab. We don't really talk about debugging tab in this course. We don't really need that. Now at the top, there's a toolbar with a set of options, typical options. You'll see software, file, edit, simulation. I'll talk about some of them when we do the modeling. Most of them you don't even need to know or deal with. But if you want to know more, obviously I always encourage you to take a look at the user guide, and the documentation of the software. If you click on that, it takes you to a website, and it has more thorough explanation about different possibilities, different options in the software, different ways. You can even connect this to MATLAB. You can connect this to Python. You can see it has C and Python interpreter. It has some kind of a connection to MATLAB. It has a connection to Julia programming language, depending on what you use for programming. If later on end up doing coding and you want to import or make your models in OpenModelica, which is much easier than doing it in other softwares. Or for instance, it's much easier to do it in Python, let's say, or MATLAB. You can make the modeling in OpenModelica and make a connection with MATLAB or Python, and do the rest of analysis there if you end up doing some research. The software itself is written in C++, so one of the reasons is fast when we run the simulations. There are multiple published work talking about how the simulations can be run much faster in OpenModelica, and the main reason is because it's written in C++, and it gives it an advantage over other, I would say, engineering simulation softwares. All right, so enough of that. Again, there's a toolbar, typical options. I'll talk about some of them as we go forward. Main thing you need to know about this welcome tab, right, this tab we are in, is that how to create a new model. All you need to do is to click on this plus sign, new Modelica class, or you can just go to file and select new Modelica class. If I do that, I have to just choose a name. Let's say for this class, code make for 11. Keep it as a model. Don't worry about the rest of the other options. And you don't need to do anything else. You can leave everything, make sure these are unchecked, these are empty, and that's all you need to do. If I click on OK, now automatically we go from welcome page or tab to modeling tab. It has a star here, meaning that this file is not saved yet. Now, so in this page, you see a toolbar, a set of tools in the top, right, below the first toolbar that we had. Now, these are typical options. You can open a model from before. We can save this model. We can save a copy of the model, and you pay attention every option or every icon. I put my or I hover my mouse on. You can see an explanation in this bar at the bottom. Right? It gives you a very short explanation about what this does. This reset the zoom. This is for zoom in, zoom out. These are to create, if you want to create specific icons, we can use these. And I'll talk about these when I make a model later on. This set of buttons here that are mainly for how to run the model, how to change the time of the simulation, etc. All right, enough about the software environment. Let's learn the rest of it through going through a couple of examples. Now let's model a spring mass system. Right, it's the first type of vibrating system we, well, the second type after the pendulum we saw. Now to do that, let me close everything. First of all, we can see my model I created. Now I have make for 11 here in my library toolbar, so it's added there. Now, if I open Modelica, I go to mechanics, right? Under translation, I go to components. Now, to make a spring mass system, right? Free vibration of a spring mass system, if I want to create such a system, I need a couple of blocks to connect them together. Well, obviously, I need a ground that the spring and mass is attached to. So that would be the fixed option. I just left click on that and drag and drop it to my environment here. Let me zoom in a little so it's more obvious that what we're doing here. It's the fixed option. Let me delete it. I want to do it again. So when I dragged and dropped it here, you see there's a pop-up window. I could even choose a name. You could just leave it as fixed one, or I can just put ground. This name doesn't really have anything to do with simulation. It's more about how convenient is that to refer to this later on. The second block you need is a spring. Drag and drop it here. Again, you can just put a name for that. I'll just put spring. If you don't, it's going to be spring 1. Now it's towards right. I have the intention of making this model upward, so I have to rotate this. I either have to rotate this or I have to rotate this one to make it a little more, I guess, aesthetically pleasing. I would say it doesn't technically, it doesn't have to be done in terms of simulation. To rotate this, right, you can just either right click and go with rotate clockwise or rotate anti-clockwise, which I think they meant counterclockwise, or flip horizontally or flip vertically. Right? Basically, Control R you can use on your keyboard to rotate objects. Instead of doing that, I'll just press Control R a couple times and make it upward. Doesn't matter, it could be either direction. I'll tell you about this arrow on the right here and what does that mean and why is it there. I have my spring. Now, the last element I need is a mass. Right? I'm modeling a spring mass system. So I drag and drop it here and I call this again, just mass. Put a name for that. Use Control R, rotate that multiple times, and again, just to make it easy to follow for eyes. Now you see these two blocks. The arrows are in the same direction. So you could model everything in the opposite way, right? You could just rotate this and make it this way, but you should make sure that also your spring is in the same direction. So these arrows are to show that when you're modeling, just make sure that your blocks, better to say it this way, make sure your blocks have the arrows in the same direction. So rotate this, make sure they're in the same direction. And all I need to do is to left click on this port or of the spring. While I'm holding down the left click of the mouse, right? Come here and go to the second port on the ground and click again. Same story. Hold down the left click, the mouse, when I'm on this port. So it creates this line or this connector. I go to the port for the mass and left click. So now I have a spring mass system connected. As easy as that. The rest is just giving the parameters. So let's say for the spring, so the only thing I have to mention is that on this software, the spring constant, which is represented by, well, you see the unit Newton per meter, is represented by C, which can be a little confusing because we use C to represent damping in our environment. Just keep that in mind. Look at the explanation for the block. It's a spring constant. So I'll put whatever I put usually for a K value, right? When we are doing the or vibration analysis. Just one thing in the software that you have to pay attention about. I'll put a spring with a stiffness of 2000 Newton per meter. That's it. And you see it's also added here. It says C is 2000. For the mass, let's say it's a mass with 10 kilograms. And here in the mass block, you can set the initial conditions. Right? You can set, it says absolute position of center of component. Right? It's a mass because we are using the software in the most simplest way. We are not really talking, we are not giving dimensions to the mass and how big the mass is. You could actually do that. But in this case, we are just giving the mass value. What is the value of the mass for this mass block? And for displacement, as it says, absolute position of center of component, the unit is meter. So we can basically sense that that is the initial displacement, S start. And all of them are under this section initialization. Right? So if I left click on that, this option comes up. I have to just set this on true and give some initial displacement. Let's say give it 0.0. And initial velocity, I can either give it 0, or I can leave it as is to be 0. Right? I'll just put it as 0. This is initial velocity V start. Right? And also you can look at the unit meter per second. All right, click on OK. And that's pretty much it. Right? Your model is set now. You have a spring mass system. One thing you need to do now, I'm going to talk about these buttons here. When you set up your model, what I suggest you to do is always do this check model. If you click on this, a window pops up. Right? This keep in mind that you connect these blocks together But by the end of the day, this is a code behind the scene. I'll show you the code behind the scene, what's going on. But this block tells me that this class, Make411, has 15 equations and 15 variables. Don't worry about what does that 15 equations, 15 variables, and 10 of these are trivial equations. Don't worry about that. Just make sure that the number of equations and number of variables are the same. When I see 15 equations, 15 variables, it's a good sign. Now, what I can do is that, oh, we only have one model, so I'm not going to talk about that. Now, to run this, right, now your model is ready. Just before we go further, we have to save this, right? Either using save button or file and save, right? Whatever you Control S is the typical way of saving. I'm just going to save that on desktop. Let's just call it Make411 MO. MO is the extension for Modelica files. Now it's saved, right? Everything is prepared. Before we run the simulation, I want to show you the code behind the scene, right? So this is just a spring mass system. You threw the blocks there and connected them together. If you go here, text view, right, keep in mind, you always have to be in diagram view at the top. There's a couple of options. Don't worry about the rest of them. You have to be on diagram view when you are in modeling tab, right? Bottom. When you're in diagram view, you can just go to text view and see the code generated by Modelica that is basically doing the simulation behind the scene. Now, these are a couple of, it's referring to specific components. It says it's under Modelica package, mechanics, translation, components, fixed ground. Right? That's pretty much it. Spring, right? The same address, Modelica, mechanics, translation, components, spring, and the constant is given here. You see, that's the 2000 I gave. Mass is 10 kilograms. That's what I gave there. And the initial values, S, I get, now you see it's set to fixed. It's set to true. Sorry, and it's 0.1. And initial velocity, V, is set to true, and it's 0. You don't need to know about things happening on this side. I just wanted to show you that basically when I'm going to go back to diagram view. When we connect these blocks, what happens is software itself generates the code in C or in its own language, I would say, which is written in C. Now to run the simulation, I'll go to simulate the Modelica class. Right? It's just simulate. If I click on that, you see this window pops up. It runs the simulation, runs the code. Again, the code is written in C, so it does some interpretation, compiling, run this whole model, right? And it says finished. Sometimes, like this case, it jumps into plotting tab by itself. Sometimes you're still in modeling tab and you have to go to plotting tab yourself when you're done with the simulation and it's successfully completed. I didn't get any error there, so we're good. Right? Message browser. Now under this, immediately you see a plot window. All right, let me just make this a little smaller and make this one bigger. Under this, you can see the displacement of the mass. Right? You have mass, spring, ground. We don't really care about the parameters under this. But if I open the mass, I can see that I have S, which is displacement. If I click on that, I can see, uncheck this, and I can take a look at velocity of the mass, depending on what I want to look at. So I'll just take a look at displacement of the mass. If I check that box, I'll see that the displacement graph shows up. Now in this graph, well, x-axis is represented by time a second, y-axis has no label, and we have a legend there. It says mass.s, meaning that's the displacement of the mass. S usually represents displacement in the software. V represent velocity. Now, to do some modifications or make some modifications to this plot, you can go to setup and make the changes here. Let's say you don't like the legend. Well, in this case, legend is only one. We only have one plot, so it can be anything. But I can just change this to displacement and keep the unit as meter. I can pick the color. Right now it's in red. I can just plot it in blue. The line type, it's in a solid line. I can use dash line, dot line, whatever line I want. I can change the thickness of the line. I can go to this. This is the variables tab. We only had one variable, and was the displacement. If I go to title, I can put a title for this plot. Title. I'll just use the word title. Vertical axis title. There is nothing here, so we can just put amplitude as meter, with meter. You can even put a footer for your map, for your plot. I'm not going to do it. Legend. Where to put the legend? We only have one plot here, so it doesn't matter where it is. And you can also identify the range. In this case, I'm going to reduce the range in negative y, and I put it as minus 0.1. If I click on OK, now it's blue. It has a title. The y-axis has a label, and we have also a legend. You could add velocity to the same plot. I could, well, it's going to be, oh, that's a good point. Now I can actually explain this. So if I click on velocity, I want to show velocity on the same plot. Right? What happens is that you see the new line, but it's totally out of range. So you go there, you either use, you use fit in view, right? Click on that. And now it's going to fit the view for you. Before I manually change the y-axis, you could even use fit view and fit the graph. Software itself finds the best appropriate range to represent these values or these graphs. You can turn on detailed graph, detailed grid that you see there is smaller grids, or you can just go with the grid that gets rid of the smaller grids if it's too crowded for you. Right? Or you can just go with no grid, depending on what kind of grid you want. You can have logarithmic scale in x and y axis. You change that, you will get the logarithmic scale. Obviously, in our case, it's not something we use. So now the legend, if I go back to setup, now we have two components. Mass S, which is velocity, displacement. I use the name displacement. Now I can click on mass V and change this to velocity. And since we have two lines, I'm going to change this to a different color and a different type of line. Let's say dash line, and use the same thickness as the other one too. Right? If I click on that, now I have displacement in blue, velocity in red. Sometimes it doesn't make sense to put everything in one plot. Right? So if you have displacement and velocity in the same plot, you see that it's hard to see how the displacement is changing. You can remove this velocity from this plot by just easily clicking on this. This case doesn't fit in view, doesn't do a good job, so I'm just going to do what I did and change the scale to minus 0.1. All right. So now let's say you want to plot the velocity separately. All you need to do is to create a new plot. Right? This is one plot. If I go up there, it says new plot window. If I click on that, the new window is going to show up. Now I can plot velocity on this. Click on this, and I'll get the velocity in this window. And you can do the same thing with setup, title, x-axis label, y-axis label, units, and even legends. Right? Now, once you're done with your plot, you can save your plot. Right? You can just go to save. Right? If I go to desktop, you can save it under PNG, SVG, or BMP, depending on what you want to save it. I'll just put it with PNG format. So I'll just put plot.png. You cannot see my desktop, but I can open it, and this is the file. Right? Exactly the plot we created. Now, you might not like the way the plots are represented in this environment. What you can do is that you can export this data, say this displacement, to Excel and plot it in Excel or any other software or in Graph. The second video that I posted about Graph, how to plot data, I actually explained how to get, when you get the data from OpenModelica, how to plot it in Graph. You can take a look at that. If you go back there to the page, here, the second video plotting data, at the end, it also explains how to use the exported data from OpenModelica and bring it to Graph if you want to put it on top of an analytical solution and make a comparison. Right, to do that, you just go to CSV, export variables. And let's say on desktop, I just use the default name and export it there. Right, it says here now it's exported on my desktop, my CSV file. If I open that CSV file, Right? If we just click on OK, that's a big one. So let me make it smaller. We can fit it here. Almost there. There you go. So you get an CSV file, right? The first column is time, the second column is mass, S, or mass displacement. Right? If I had the velocity in the same plot, I would have had this third column here as velocity. Right? Depending on how many variables you have in that plot, it's going to be exported here. And you can use this and import this to graph and plot it there. Again, in that video, I slightly explained how to do it. You have to remove the first row to have an easier time when you import it to graph. All right. So it's the whole story. That's all you need to know about the software environment. Keep in mind the mass, the displacement, the velocity when you want to plot, right? Just you can put it separately or together. You can manage the graph. Now the simulation was run for 1 second if you paid attention. And I didn't say anywhere how long do I want the simulation to be run. To change this time, right, sometimes you have to run the simulation obviously for more than 1 second or less than 1 second. If we go back to modeling tab and click on this icon S, simulation setup, we can set this up. Right now the stop time is 1 second. Right? We can set this up to 5 seconds. Well, let's just go for 2 seconds. And the number of intervals, usually use some big number. Right? It's enough, should be enough number of points that when you plot the graph, it doesn't look very broken. Right? You have enough points to have a smooth plot. If I click on OK, it does immediately start the simulation again. It runs the simulation again for 2 seconds. It does the compilation. Now it says it's complete, and it goes back to this plot. Now, if I do the fit in view, now you see the simulation is for 2 seconds. Right? I have more data. Same story about this one. So we can change the simulation time. All right. This was just for a spring mass. Now, I can delete this, or I can just keep it on this side and put the second model here. You can make as many models as you want in the same Modelica, let's say, class. Right? I'll just delete this to make things less crowded. I'm going to make a spring mass damper, free vibration of a spring mass damper. I'll do it a little faster this time. We're familiar with a couple of elements, so obviously fix has to be there as a ground. I'll put it there, make it a little bigger. A mass has to be there. I'm going to use Control R to turn it this way. Let me just go to plots and close these so later on things are not messy. And I'm going to delete the results for this. You could have it there. It doesn't really matter. You're going to get a set of results. Now, the mass, the ground. Now, in this time, because I'm using I'm modeling a spring mass damper, I'm going to use spring damper element. You see, it's already there. All you need to do is just drag and drop it here. I'm just going to keep the name spring damper. I'll change it a little bit. Click OK. I'm going to use Control R, rotate that, make sure the arrows are in the same direction. Then I connect them. I left click on this. Move it all the way to port for this one and left click again. Left click on this one, hold it, go to the port for the mass and then left click again. Now they're connected. Let's give the values. Let's say I have a 10 kilogram mass again, and let's go with the initial values of very similar. Initial velocity, displacement of 0.1. This time I can even give an initial velocity of 1 meter per second instead of 0. On a spring mass damper, now I have 2 components that I can put. Spring constant. All right, so let's go with the same spring we used before, 2000. And a damper. Now you see the damper is represented by D here. So it's a little difference between the way, there is a bit of a difference between the way we represent these elements in the course and in the software. Software use C and D, we use K and C. So it can be a little confusing, I admit. Let's put the damper of, with the viscous damper of 50 Newton second per meter. Right? And you don't need to change anything else in this block. And that's pretty much it. Right. We're going to run this simulation. Let's run it for 5 seconds. I'm not sure what gives the best result. Let's just test 5 seconds. So I'll put it on 5 seconds. Well, before that, let's double check. Let's check the model. So we have 19 equations and 19 variables. So we're good. I'm going to save this. Now I'm going to go and to simulation setup. Let's do it for 5 seconds with 700 steps or intervals and click OK. So software does what it does, right? We have the behind the scene code. Obviously, you can take a look at this, the code for this software, for this model. So it does the simulation. We're going to get, again, a set of results. So I use mass, spring damper, and ground. Again, I can go and take a look at the displacement of the mass. Maybe 5 seconds was too much. We can run it for 2 seconds and see a better result. But now you see the initial displacement, obviously, is as 0.1. The velocity, there is a velocity there because there is a slope. The line has a slope at the beginning, so there's some initial velocity. And because it's a damped system, after a while it approaches 0. And you can do whatever you did the previous plot, right? Change things, change the grid, save it as a plot, export it as CSV. You can take a look at velocity, both of them together, or just plot the velocity in a separate window. All right. Hopefully I didn't forget anything here. Let's do another model. Right? This was just a spring mass damper, right? Free vibration. Now, what if I do a spring mass damper force vibration? What the topic we covered in last class, right? Let me move things around a little bit. All right. So in this time, I'm going to keep this model here, so you see what happens if you have multiple models. Right? I could remove it, and I could go to plotting and unload and remove this. But I'm just going to, in this case, because that's something you might have to deal with, so I'm just going to keep it that way. I'll go back. Right? Now, I want to make a force vibration simulation, right? Spring mass damper again. So I'll bring another mass here. Let's just do it again, and just want to do it while I'm importing it. Call this mass 2, because I already have mass already there. So I'm going to rotate it, keep it upward, everything. Also, you know what? Let's do it this way. You can do it in either direction. The way you arrange these does not change the results you get. I'll have my since it's a force vibration, a spring mass damper, I'm still going to have those 3 elements I used before, right? So I have a spring mass damper. And let's call this spring damper 2. The same direction as the arrow is in the same direction. And I'll bring a support fixed. And let's put this, name this ground 2, so I know it's for this model. I use Control R, rotate it this way. I'm going to connect these the same way I did. So I'm going to left click, hold it, go to the next port, left click again. Left click, hold it down, go to the next port, left click again. So now I have my, let me move it a little this way. Now I have 3 components. Now, since this is a force vibration, I have to define the force, right? What kind of force is applied to this mass? Remember this spring mass damper force vibration? We had the same system as spring mass damper. There was a harmonic force applied to this mass. So to get the harmonic force, I have to go to blocks library. Right? If I expand this library, there are other sub-libraries there. Under those sub-libraries, I'll go all the way to sources. It's a source, right? Type of source that we are using. So if I expand the sources library, right, under blocks, sources, I have different types of inputs. A lot of them, general things that you are not going to use. But let's use a cosine function, right? Because what we did in a course, we use a cosine function as an input force. Right? Drag and drop it here. And let's call this cosine input. So let me rotate the block a little bit. It's easier if it's this way. Let me move these that way and select these. I'm just using left click and selecting everything, dragging them a little bit farther so these two are a little, there's more room here. Now this is a cosine type of function. How do you define this input now? I'll tell you a little bit in a little bit, but let's just be done with all the elements we need. So now you can't just connect these directly to this. Right? That is not going to give you the right answer or a right way of doing the simulation, because this I deleted that by just selecting the line. Just good to explain. So I clicked connected this. What you can do, you can either right click on the line and delete it, or you can just select the line and press delete on keyboard. Now this is just a signal. It's a cosine signal the software generates with some given amplitude, frequency, and other properties you will see I'll talk about. But in order to make the software understand that this is a physical signal, but I want you to interpret that as an input force, I need another element in between, right, to interpret this input signal as a force. To get that element, I'll go back to mechanics again, the same library that we were using. Right? Go to translational, right, library and sublibrary components. Under the components, sublibrary sources. So remember, these sources are different from the other sources. The other sources is a general library that gives, you can generate any type of signal you want. These sources are specifically for mechanical engineering systems, or mechanical systems, I would say, not mechanical engineering systems. Now here, I know that this signal has to be interpreted as force, so I'm going to choose force as the connector. I'm just going to force, you can call it force connector. Maybe it's easier to read if I write. Now I have something that I can use. Well, I'm going to rotate that. Control R 2 times. Keep in mind that the blue side should be towards the signal, and this port should be towards where the mass is when we connect it to mass. So I left click on this signal. Now I can connect these. The top at this port for the signal block, and drag it and left click on this one. Again, left click on the tip of this force element and drag it. Left click again, connect it to mass. Now it's connected. See, whenever I move it, it's connected. That's how we can check if it's connected. Now let's start giving the parameters. I'm going to start with what is familiar, right? Spring mass damper. Well, we did it before. Let's just do this. Use the same parameters. Let's use the spring constant of let's use 2000, and use a damper of 30 Newton second per meter. That's it, right? So spring mass damper only needs spring constant and mass damping constant. Mass, if you double click on that, I'm just going to use, I guess, the same mass I give, 10 kilograms. And let's go with initial displacement and initial velocity as before. So initial displacement of 0.1 and initial velocity of 1 meter per second. This connector has nothing to set. It's just there to connect the signal to this physical system. So there's nothing to set there. I'll just leave it as is. Now, if we go to physical signal, if I double click on this, here you have a representation of the signal on the bottom right. Right? It shows the offset, what the offset is, what the start time is, what the amplitude is. This is the time signal, and this is why it is the value. Remember when we were defining force input, we were defining as F naught cosine omega t. Right? F naught here would be the amplitude. Since this is going to be interpreted as a force, obviously the amplitude we give would be the F naught. Let's give an amplitude of 50 newtons. Now, important frequency in this software is always in hertz. So whenever you know your frequency, make sure you convert that to hertz. Right? How do you convert it? Omega is equal to 2 pi f. Right? If you have the frequency in hertz, you multiply it by 2 pi, you get the frequency in radian per second. If you have the frequency in radian per second divided by 2 pi, you get the frequency in hertz. So in this case, I'm going to give 2 hertz as the frequency. Now, there are other options. You can add a phase. Well, in our case, we did not really, let me see if I can write it. We did not really talk about the type of force with some phase, input phase or some offset, but the options are available here. Right? If you think about phase and offset, you can think of them as, let me see if I can write here. Think of them as, you can think of this as F naught cosine omega t plus phi. Right? And that phi would be the offset phase. Now, you can either do it as in degree or in radian. Again, in our case, the force we talked about, or at least mathematically we found the solution for the input force, was F naught cosine omega t. Right? This omega, remember, it was in radian per second. So if you want to write it in terms of this setup, would be F naught cosine 2 pi f t, right? F being in frequency in hertz. So I can leave the rest 0, right, or empty. Phase is 0. There is no offset, right? My cosine function starts from, so the offset would be, let me see if I can explain this. The offset would be, well, we can see it already here. Not starting from 0 in y-axis. So let's say you start from here when you have a cosine function. Some offset added. And you can also set the start time not to be 0. You can start from like after 10 seconds of running the simulation, or 0.1 seconds. You just leave everything else as 0, because you want to be very similar to what we talked about in the class. All right. Move around. So I gave a force with F naught 50 and frequency 2 hertz. Remember, this is interpreted as a force because I had it connected. So if I click on OK, I think we said, let me double check. If I check the model, we have 44 equations and 44 variables. So number of equations, number of variables are equal. I'll save this model. Again, you can always go to view text view, and see the models, right? Now we have 2 models here. The first one is this part, and the second part is, it starts from here. Right? It's obviously more messy, and the connections are mentioned here, how they're connected. And you don't need to worry about that, but just so you know, the code is generated and it's there. Let's see if we get any error or we're good. Let's run this for, why not, 5 seconds. Seems like we're good. So once the simulation is done, we go back to where we were, right? Now keep in mind, now I have 2 masses, mass and mass 2. I have 2 spring damper and spring damper and spring damper 2. I have ground and ground 2. I have every components I had. So don't get confused if you have more than one model. You could just easily remove this and make this model by itself in this modeling environment, so you wouldn't have this mass, spring damper, and ground elements anymore. But because I have both of them in environment, I just wanted to see what happens if you have multiple models in one environment. Now I'm going to create a new plot. This is old. This is for previous systems. I'm going to create a new plot. I'll go to mass 2. I want to see the displacement of the mass. This is the displacement of the mass, right, for 5 seconds. Now, remember, when we were talking about force vibration, we said force vibration of a spring mass damper, what happens is that the system response, which is this S right now, is, let me write, I can write here. We said the system response is a combination of 2 parts. We have a steady state response and we have a transient response. Now the transient response was related to a e to minus zeta omega n t part, the exponential decay kind of thing. And you had sine omega t plus phi. Hopefully I remember this correctly. This was for transient response. And then you had your steady state response, right? It was the second part of the whole system response. The transient response was something that was approaching zero. And the steady state response was just some, as it name says, a steady state, steady response. The combination of these two were giving us the system response, which has both elements in it. The initial part, you see some effect from the transient response, and after that, the whole response is dominated by a steady state response because the transient approaches zero. The same story looking at this plot here, right? If you look carefully on this plot, right, we have some transient response at the beginning, or the beginning part that is affected by transient response, and the rest that is mainly dominated by steady state response. This is the same story that we had from before. Now keep in mind here again the same story. You can set up your plot, change the legends, change the grids, put titles, set up the ranges. Specifically encourage you when you use this, if you want to use and plot it here, I encourage you to do it. Right? I want good plots. You've noticed that by now. I'm sensitive about plots. The better way, which I highly encourage you to do, is, as I explained in that video, is to export this data as CSV file. And let's just use the same variable here. Open it. Export this as a CSV file, and then modify it and use graph software for plotting. Again, in that video, I explained how to export, when you export the data as a CSV file from Modelica, OpenModelica, how can you import it into GraphSoft? So in this way, you can make a comparison to your analytical solution and numerical simulations. Now remember, I did here is force vibration of a spring mass damper. I could make a simulation for force vibration of a spring mass damper instead of a spring mass. Sorry, I got confused. I could make a simulation for a force vibration of a spring mass damper instead of a spring mass system. I don't know why they say instead of a spring mass damper. Right? All I needed to do is just to replace this spring damper element. Right? If I remove that, delete that, I could just replace that with just one spring, right? And it would be the spring mass dampers, spring mass system, force vibration of that. I could use a different force input, right? I used cosine. I could use exponential input. I could use pulse. You'll see later on when we talk about non-harmonic excitation. I could use a step input. I could use a sine function as input for a force. This is enough for now about the software. Later on, I'll post the second third project next week. I hope on Monday. And for that project, you need to use OpenModelica for your simulation. So any added explanation or something extra needed you need to know, I'll just make